So the Pi 5 is the most powerful Raspberry Pi that's currently on the market, and with the increase in power comes an increase in heat. While there are already quite a few cooling solutions available, I wanted to tackle this project on my own, and design a cooling system that can be modularly scaled up to ridiculous proportions. I've also always wanted to try and cool a Pi with a Peltier cooler or tech. So today we're going to try and push Pi cooling further than I've ever done before, hopefully getting the Pi CPU down to below 10 degrees. Ice tower style coolers like this have been around since the Pi 4 and are generally already considered overkill, even for a Pi 5. The problem is that there's no easy way to attach a tech to one, or to any other standard Pi heatsink for that matter. So I started out by designing a new enclosure in Fusion 360. Unlike my other enclosures, which are designed to be 3D printed, this one's designed to be CNC machined from aluminium. And best of all, it's designed with a couple of modular brackets and blocks, which allow me to step cooling up from a simple passive heatsink, moving through adding fans to a full-size CPU cooler, and finally the two tech configurations, which is where things get a bit ridiculous. First and foremost, I want to see how close I can get the Pi CPU temperature to 0, but I'd also like to run a Geekbench benchmark at the two extremes to see if there's any difference in performance. After all, if there's no performance benefit, then it's not really worth doing. Next, I needed to get the enclosure components made up. Now I could have done what I've done previously and made them up on my Carvera Air, but milling this amount of aluminium would have taken a long time. So I got PCBWay to assist with making up the parts. I've previously used them to make up circuit boards for my electronics projects, so when they reached out to ask if I'd like to try out their 3D printing or CNC services, I thought why not? They make it really easy through an online order form where you upload your files and then select a couple of options for tolerances and finishes. I went for an anodized finish, which was their recommendation, and I'm really glad that I did. 2 weeks later, the parts turned up, and man did they look better than I was expecting. It's really cool to see your 3D CAD model turned into something that looks and feels like a premium product. The anodizing really makes the components look much better than I'm able to produce. I was then quickly sobered by the thought that these components look amazing, but being a first run, I've never actually tried assembling them. And if you've tried designing your own 3D printable parts, then you've probably discovered that things don't always work out the way they look in a CAD model. So next I moved into assembling the basic Pi setup in the case. It's designed to house an NVMe SSD on a hat underneath the Pi. For this I'm using a Pomeroni NVMe base and a Lexar NM620 NVMe SSD, which I've pre-flashed with Raspberry Pi OS Trixie. That's installed onto some brass standoffs screwed into the base. Next, the Pi is installed above it, and the drive can be connected via the PCIe FPC connector. I've used a 16GB Pi 5 for this build, as higher memory variants tend to be more stable for overclocking, because they're usually more recently built, although there is still a bit of silicon lottery involved. I then trial fitted the open lid and empty fan cover, and I'm really happy with the results. I'm actually quite keen on just using this as my main Pi case going forward. So now let's move on to testing. For each setup, I'm going to run the same stress NG test for 15 minutes, which is usually long enough to fully heat soak the cooler and allow temperatures to stabilize. I'll do the test at both the stock frequency of 2.4 GHz and at an overclocked frequency of 3 GHz. I'll also do a Geekbench run for the first cooling solution that can make it through the 15-minute stress test at 3 GHz without thermal throttling. I'll then repeat it for the solution that achieves the lowest stabilized temperature. For each test, I'm only changing the cooler. Other than that, I'm keeping the same Pi, NVMe drive, case, power supply and software. First up, let's start with a simple passive aluminium heatsink, which I don't expect to do very well. These are usually fine for light loads a little above idle, but for sustained loads or any form of overclock, you really need a decent cooler on the Pi 5. At the stock 2.4 GHz, the CPU temperature started out at 58 degrees at idle, and it actually managed to run for almost 5 minutes before the first thermal warning. At 5.5 minutes, it started thermal throttling. The CPU then stayed around 82 degrees for the remainder of the test, but with the CPU running at a reduced frequency. This didn't bode well for the 3 GHz test, but I ran that anyway just for comparison. This test ran for about 1.5 minutes before thermal throttling, and the CPU temperature then stayed around 85 degrees. so I stopped the test after 3.5 minutes to avoid damaging the Pi. Next, let's see how adding a simple PWM controlled fan to the top of the enclosure helps it out. These fans typically use around 1/4 of a watt, so they're a pretty low power cooling solution. The one that I've installed plugs into the CPU fan port on the Pi, which by default turns on around 50 degrees and then scales up to maximum speed at 75 degrees. At 2.4 GHz, straight away we can see we've now got a lower start temperature, around 50 degrees. This run didn't thermal throttle, and after 15 minutes it had stabilized around 59 degrees. At 3 GHz, the starting temperature is a little higher at 55 degrees, and again it didn't thermal throttle for the duration of the test. This one stabilized around 66 degrees. So adding a simple fan is actually quite effective. Interestingly, I assume because of the fan curves, the CPU temperatures actually ran a little hotter at the beginning, and then reduced once the fan had sped up. Since this cooling method was able to complete the run, I then ran the Geekbench 6 CPU benchmark. This managed a single core score of 1062 and a multi-core score of 2271. These are going to be the scores to beat for the final setup. Now let's move on to our 120mm tower cooler, which is where things start to get ridiculous. So we've got this block that now mounts onto the Pi, and essentially acts as a large heat transfer block. I've used thermal paste for the CPU and pads for the surrounding components. This removes heat from all of the heat producing components on the surface of the Pi and transfers it to the base of the tower cooler. The cooler then bolts on top of the case and makes contact with the top surface of the block, which is sized similarly to a PC CPU. And this already looks a bit nuts. For this setup, I'm powering the fan from a separate 12V power supply, and I'll do the same for the techs so that we can see exactly how much power our combined cooling system is drawing. The dual fans draw 8 watts combined, so about the same as the Pi does at full load. As you'd expect, this cooler performs really well. At 2.4 GHz, temperatures start out at 23 degrees and stabilize at just 25 degrees under full load, so barely any difference between idle and under full load. At 3 GHz, temperatures started out a little warmer at 24 degrees, and it stabilized at 27 degrees under full load. So both significantly better than the small heatsink we tried first. Noise levels are also really low because of the large 120mm fans. Although being cheap unbranded fans, they could be a little quieter. But now we're starting to run into a limitation. The cooler can't cool the Pi below ambient temperature in my workshop, which is currently around 23 degrees. So let's move on to our active cooling options. I've got 2 Peltier Coolers or techs, and these can each do around 30 watts. We've also got 2 options to connect them to the Pi. The first is to connect them in parallel using this adapter block. A small fan and heatsink then cool the hot side of each cooler. This setup provides roughly 60 watts of active cooling capacity. It's booted up at 2.4 GHz, so now let's turn on the techs and fans and watch the temperature drop. Because of the potential for condensation, I'm only going to run the techs for a minute before the test to cool the block down, and I'll let them run for a few seconds after. I don't want to risk drowning the Pi before I've tested all of the options. After about half a minute, power draw is stabilized at just over 60 watts, but the results are not as good as I'd hoped for. On the CPU side, temperatures have dropped under ambient, and on the opposite sides of the coolers, the heatsinks are really hot. The big downside of this arrangement is obviously efficiency. We're consuming 60 watts in cooling, while our Pi is only drawing around 8 watts. With this configuration, at 2.4 GHz we have a starting temperature of 19 degrees, and this stabilizes at 18 degrees under full load. Because of the thermal mass of the large heatsink block, the techs take a while to cool it down. This leads to our loaded temperature gradually reducing to become lower than the initial unloaded temperature. So now stepping up to 3 GHz, we have a starting temperature of just 17 degrees, and it stabilizes at 21 degrees under full load. So it's still running below ambient at full CPU load while overclocked to 3 GHz. But for a cooler that's using over 60 watts, that's a pretty disappointing result. I don't think these small heatsinks that came with these techs can actually handle their heat load, and the hot air from them is being blown down onto the Pi enclosure, which is adding to the Pi's heat load. I did start getting some condensation with this setup on the top of the heatsink, which was probably around 15 degrees, so it could get much worse with the next setup. With that test done, the final configuration is to arrange the coolers in series, called cascading. So instead of running the two coolers alongside a central block, I'm now stacking them so that the first cooler cools the second, which then cools the heatsink. On top of the stack, I'm adding the large CPU cooler to keep the hot side of the top tech cool. This configuration can move less heat as total throughput, but it should result in a higher temperature difference between the two extremes. I think that this setup will have the highest potential cooling performance, but it also has the highest complexity, and there's the risk of condensation forming if temperatures drop below dew point, which is currently around 14 degrees. With this setup, I initially pushed the power draw up to 70 watts, but I managed to crank it up a bit more, up to 82 watts, because the CPU cooler performed much better than the small heatsinks. With our most extreme cooling solution, at 2.4 GHz, we have a starting temperature of just 10 degrees, and this stabilizes at 8 degrees under full load. Finally, stepping up to 3 GHz increases the starting temperature to 15 degrees, and it stabilized at 11 degrees under full load. So we're now running at over 13 degrees less than ambient at full load and with overclocking. We also have a pretty ridiculous looking Pi. Condensation's also already quite bad. You can't see it on the outside of the enclosure, but you can see droplets have formed on the cold heat block. But the Pi is still running, so I decided to try my Geekbench run. This managed a single core score of 1066 and a multi-core score of 2311. So it is slightly better than the fan cooler, but under 4% difference, so for the additional power draw it's definitely not worth it. Putting the logged results side by side, we can see some interesting trends. Passive cooling does okay for short bursts, but eventually heat saturates the heatsink and becomes ineffective. Forced air cooling using a small 30 to 40mm fan provides the best balance of performance, simplicity and power efficiency, and you can PWM control it to also manage noise. The tower cooler delivers excellent sustained performance and allows higher overclocks, although it looks pretty ridiculous doing so. And while the Peltier setups can achieve lower temperatures, they require significantly more power and introduce a lot more complexity into the system. The stack tech configuration produced the lowest temperatures overall, but it came at the expense of power draw that's almost 10 times that of the Pi it's cooling. So was any of this actually necessary? Definitely not. As you can see from the Geekbench results, there was only a marginal improvement in performance between the simple small fan and heatsink and the stacked Peltier arrangement that I tried at the end. And this was with over 80 watts increase in power draw. This is also supported by the stress test results. You can see at the end of the fan run that the Pi had performed 4,323,743 bogus operations in the 15-minute period. And with the stacked Peltier test, this only went up by 42 operations, which is less than 0.1% improvement. As long as your cooling solution can stop your Pi from thermal throttling at whatever frequency you're running, then any additional cooling capacity doesn't really provide any benefit. Realistically, a good heatsink and fan or a small tower cooler is probably the sweet spot for most people. In fact, in my past test, the $5 active cooler that was designed for the Pi 5 does a pretty good job at cooling an overclocked Pi too. In any case, experimenting with these cooling options was fun and interesting. It shows the advantages and limitations of active cooling on small computing platforms. If you'd like to see more extreme cooling experiments, or if you've got ideas for other completely unnecessary upgrades I should try, then let me know in the comment section below. And if you enjoyed the video, don't forget to like and subscribe, and thanks for watching.